In this video, we will discuss more ways to evaluate a limit of a function, right? The limit of function at a point. So the second method we have based on a very natural observation of the definition of limit, right? Recall the limit of a function at a point really doesn't depend on the function value at the point. It totally depends on the function value near the point A here, right? When you have two functions, which means if you have two functions, they are always equal besides the limit point A, so the limit should be same, right? So this is basically very natural, right? Easy observation we have. We call this a fact. So if you have two functions, right? So if you have two functions, f and g, they agree everywhere, but at A, right? F of A, G of A doesn't match. They don't match anymore in the sense of evaluating the limit, right? So then this implies the limit should be same as x goes to A, f of x equal to as x goes to A, g of x, right? This gives us a way to evaluate limit. So if you have a function, you cannot plug in A because f of A or g of A is undefined. You can try to cancel the zero factor in the denominator to get a new function in which you can plug in your A here, right, to get the limit. So let's see a couple examples. Let's see example. The first one here, let's see this, right? As what? As h goes to 0, right? H is our independent variable. So this is 2 plus h to the power 3 over minus h over h, right? Now you can see that. Let's give a short discussion here. So this is a rational function because both numerator and denominator are polynomials, right? This is a rational function, very typical rational function. A domain of this function, domain, is kind of clear, which is everything but 0 because denominator is h, so the domain of this function is everything but 0, which is negative infinity to 0, union with 0 to positive infinity. Or you can write this as all the x, but x cannot be 0, right? So that's the domain of this function, which means our first method fails. You cannot plug in 0 because if you plug in 0, this function is undefined, right? And so if you try to plug in 0, right? So you can see that as h equal to 0, right? Numerator 2 plus h to the power q 3 minus h also equal to 0. So we have a short notation for this kind of limit, which is 0 over 0. And because as h goes 0, both numerator and denominator goes to 0. So that's 0 over 0 doesn't mean we are dividing 0 by 0. That means we have a limit as h, as your independent variable, goes to the point, both numerator and denominator go to 0. So that's a short notation for if that happens. So this is undetermined. So this is undetermined. And so just one more time, this 0 over 0 is not dividing 0 by 0. Basically means you have a limit of a quotient as your variable goes to the specific point, then both numerator and denominator goes to 0. So that's the meaning of 0 over 0. It's not actually dividing 0 by 0. So that's a short notation for this kind of thing if that happens, right? So this is clearly 0 over 0 as h goes 0. And so we cannot plug in 0 because we have a factor which is h in the denominator, right? So we want to cancel that h, then you can plug in 0. So what we do? We use pure algebra, right? Try to factor h out from the numerator, right? Then you can cancel that. How do we do that? And there's not much we can do for this example. We just factor out 2 plus h to the power 3, right? If you try to do the factor, you get IH plus 12h plus 6h squared plus h cubed, right? Just the factor, the square, then multiply by h plus 2 one more time, you get this. Then minus h over what? Over h, right? So if you try to simplify the denominator, 8 canceled, right? H goes 0, so these two numbers are canceled. Then you have a common factor, which is h. So which is h times 12 plus 6h plus h squared over h, right? Now you can cancel our 0 factor, which is h here. Now in this new form, this new function is a polynomial, right? Which is 12 plus 6h plus h squared. So we can apply our first way, which is directly substitute h by the limit point, which is 0, right? So plug in 0 directly, you get this is 12, right? So that's how do we evaluate this limit. So you are starting from a function. If you plug in 0, you get denominator equal to 0, right? In the same time, if you plug in 0 in the numerator, the numerator also is 0. You get a 0 over 0 kind of limit, which is a quotient. Both numerator and denominator go to 0, right? And so they both go 0, which means maybe somehow you can cancel the 0 factor on the denominator, right? Fortunately, we can do that in this example, right? We factor out 2 plus h cubed and simplify that. You get a function contains h as a which contains h as a common factor. You take out h, cancel h, you plug in 0, right? So this is what we did. Now let's see another example we have. Second example here is we are looking for the limit of as again here as h goes, no, t goes 0, t here the limit goes to 0, you get square root t squared plus 4 minus 2 t squared, right? So this is basically another fraction, right? And so you can see that if you plug in 0, so there's a function, right? And the function here, domain is also everything but 0, right? The function, so which means you cannot plug in 0 directly, right? So if you plug in 0 on the numerator, you get 0. If you plug in 0 in the denominator, that you get also get 0, right? So this is also a 0 over 0 type of limit, right? And so we just want to somehow, right, cancel t squared, which is our 0 factor, and then plug in 0, right? So that's 0 factor in the denominator. We want to eliminate that 0 factor in the denominator. Then we want to plug in the limit point of t, which is 0, right? You get the answer. The question is, how do we do that, right? And for sure, you cannot factor t squared out on the numerator, which is impossible. Square root minus another number, which is hard to factor for sure, right? So in this case, we have a new way to handle that, which is multiply by the conjugate, right? So if you have a difference or sometimes sum of two terms, the conjugate will be the change the sign of the change sum to difference or difference to sum, right? So we know that we have a good formula, which is a plus b, a minus b equal to a squared minus b squared, right? So which means one of these is a conjugate of the other, right? A minus b's conjugate is a plus b, and a plus b's conjugate is a minus b. So it's if it happens that the new one of them contains square root, you can use this formula to get rid of square root, right? If you get rid of square root, maybe you can take out common factor. So that's our strategy, right? So by our discussion, the conjugate of the numerator is quite clear, which is square root t squared plus 4 minus 2, then times square root t squared plus 4, then plus 2. Over, we don't want to change our function, right? We do the same thing in the denominator, times square root t squared plus 2 plus 4, then plus 2, right? So by apply our formula here in the denominator, this is as t goes to 0, t squared plus 4, right? Because square root, take a square, you get the term inside. Then minus 2 squared, which is 4, over t squared times square root of t squared plus 4, then plus 2, right? And now the numerator is basically t squared, right? After we do the simplification, you get this is as t goes to 0, t squared over t squared times square root of t squared plus 4, then plus 2, right? So this factor here, they cancel each other, right? So you get a good function, which when you plug in 0, good means if you plug in 0, you don't have 0 anymore in the denominator. It's a t goes to 0, 1 over square root of t squared plus 4 plus 2. So this new function, the domain is all real numbers, right? You can plug in 0 directly. So this is 1 over square root of 4 plus 2. So this is 1 over 4. So this is how do we use our second way to evaluate the limit. The way here is basically try to cancel the 0 denominator in the the 0 factor in the denominator either by try to factor the numerator, right, or try to multiply the numerator by its conjugate.